Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing Layer 2 security and loop prevention. In this lesson, we'll be covering Spanning Tree Protocol. In the previous lesson, we reviewed briefly what a forwarding loop is, how it occurs, and why they're bad for our network. We also reviewed some basics about the flavors of Spanning Tree Protocol, or STP. In this lesson, we'll be taking a much deeper dive into the original STP, defined in the IEEE 802.1d standard. First, let's do a quick review of the high-level steps STP uses to create a loop-free topology. The first thing STP speaking switches do when they boot up and STP initiates is they transmit and exchange BPDUs, or Bridge Protocol Data Units. These BPDUs include, among other things, the bridge ID of the switch that the transmitting bridge believes to be the root bridge. Once a superior or lower bridge ID is received, then the switch will believe that the superior bid is the root and will begin transmitting BPDUs with that superior bid instead. Once all switches agree on which bridge is the root, or which bid is the most superior bid, the root bridge is then said to have been elected. Each switch then independently calculates the lowest cost path to the root bridge using the port cost and port priority information received from the neighboring switch's BPDUs. The port with the lowest metric cost path to the root bridge is assigned the root port role and transitioned to a forwarding state. Once the port states and roles are established from the completed shortest path computation, the spanning tree network is said to be fully converged. So, we've mentioned port states a few times, and know that at least forwarding is one of them. Though, what are the other port states? In 802.1d Spanning Tree Protocol, ports may be in one of the four states listed here: blocking, listening, learning, and forwarding. On the right of each state here, we can see what function a port in that state would perform on user traffic and BPDUs. It's worth pointing out that BPDUs are always received by the switch and processed in every state. We'll step through the convergence process a little later in this lesson, though first, let's walk through each of the port states. When a port is in a blocking state, all user traffic is dropped because the port is not being used. When a port is transitioned from blocking to forwarding, it must follow this order of port states from top down. This means when a switch decides it needs to transition a port from blocking to forwarding, the port will first transition to the listening state. In this state, the port is discarding user traffic still and is simply waiting 15 seconds to make sure the topology doesn't change again before moving to the learning state. If the topology does change again, as indicated by BPDUs received, then a new calculation would occur and potentially result in the port transitioning back to the blocking state. You might have guessed, in the learning state, a port is learning the MAC addresses seen in the source address of the headers of ingress frames. Frames of user traffic are still being dropped for another 15 seconds, while we learn what MACs are reachable on that port. This allows the bridge to update the forwarding table after a topology change, so that frames are more likely to reach their destination successfully once the port is transitioned to a forwarding state. Finally, in a forwarding state, the port is fully operational and forwarding traffic, and of course, it is still processing BPDUs. This is the final and stable state for a port. It will stay in forwarding state until the topology changes such that it becomes blocked. You might be thinking, 30 seconds to transition a port to forwarding state after a topology change? That's slow. And you are absolutely correct. 802.1d spanning tree protocol is quite slow to change states, and therefore converge after topology change events. 30 seconds is so slow, in fact, that protocols like DHCP for IP address assignments to end hosts can fail due to not receiving a response in time. Though later we'll discuss a feature which can be used to mitigate this particular issue. This is why you will seldom see 802.1d STP deployed in modern networks, in favor of faster converging protocols. Since the BPDU is the key piece for spanning tree protocol to function at all, let's take a closer look at the format of that data unit. In the following slide, we'll review the byte field format of the 802.1d BPDU. Here, however, we see the frame's overall format. In 802.1d, there are not any distinctions between VLANs. Only a single spanning tree topology may be present at a time, and therefore all VLANs configured will have the same resulting converged topology, regardless of the logical topology that may be created by the individual VLAN. The destination MAC address of these BPDUs is the multicast address reserved for STP, shown here. The source address, however, is the MAC address of the port that is transmitting the BPDU. Now, let's take a closer look at the contents of the BPDU. Before you get worried about memorizing the format of the 802.1d BPDU, the JNCIS ENT exam is not likely to have any questions regarding the number of bytes in each field of the BPDU. I included this information, though, as you might be interested to take a look at the inner workings of spanning tree protocol. The number in the brackets here are the number of bytes long that each field is. The protocol ID is a fixed value at all zeros, representing the 802.1d protocol. Also, for 802.1d, the protocol version is all zeros. There exists two types of BPDUs, configuration BPDUs and topology change notification, or TCN BPDUs. When first converging, configuration BPDUs are sent and this field is set to all zeros. For flags, only 2 flags are defined among the 8 bits in 802.1d. The rest are simply just reserved. The root ID is the bridge ID, or BID, of the bridge that the advertising switch believes is the root bridge in the topology. Recall that this field will be updated as each switch receives a superior BPDU, causing it to believe that a new bridge is the root. The root path cost is the metric cost to reach the root bridge across the link that the BPDU is sent on. This is summed by each advertising switch, allowing for the total path cost to be easily calculated by the receiving switch. The bridge ID and port ID are populated with the values of the local bridge and port ID of the switch sourcing the BPDU. The message age is the age of the configuration BPDU, while it propagates through the network. where the max age is the maximum time the receiving switch should store the information in the configuration BPDU before it expires. This aging mechanism is what allows for STP to reconverge automatically if the root stops responding while the physical interfaces remain up. The hello time is, as it sounds, the interval that the BPDUs will be transmitted in, as the configuration BPDUs are used as a sort of keep alive by the root. And finally, the forward delay is the time to wait to transition port states. Here, we just have a different display format of the same information. The 802.1d BPDUs are 274 bytes long. This field here is 32 bits wide, with these dotted lines indicating that the field extends into the next row. So, now that we've seen what the contents of these BPDUs are, let's review the process switches follow during initial convergence and reconvergence during topology changes. When a switch first powers on and is initiating STP, it will begin transmitting BPDUs. It will populate the root ID field with its own bridge ID, effectively declaring itself as the root bridge. The switch will continue believing it is the root of the network until a better or superior BPDU is received. Since the priority value in the bridge ID are the most significant digits, the switch with the lowest configured priority value will win the root bridge election. If multiple switches have the same priority, the lowest MAC address will win the election. Once the root bridge is determined, all switches that aren't the root will calculate which connected port has the lowest metric cost to the root. We know that the cost to the root bridge is also included in BPDUs propagated in the network. This is the information used to determine the lowest cost path from each switch to the root. Though the metric cost for the port speed, shown here, is only added to that cost in the BPDU by the receiving switch on ingress of the BPDU. Each designated switch in a converged topology will have a single root port and potentially one or more designated ports. The root port is the port metrically closest to the root. If there is a tie between two ports, the port which received a BPDU with a lower port ID will be declared the root port. The other end of the link from a root port is a designated port. Designated ports, as well as root ports, are transitioned to a forwarding state, and any other ports that are not a root or designated port are placed in a blocking state in 802.1d. Once all port states and roles are determined, the spanning tree is fully converged. In a converged state, only the root bridge transmits BPDUs, and will transmit them every hello time, defined in the BPDU originated by the root. The maximum amount of time that may pass for an STP topology to converge is shown in this calculation here. 2 times the forwarding delay plus the max age timer. Recall that these times are both included in the BPDU originated by the root. The time set by the root bridge's BPDU is the one which should be used in this calculation. By default, the forwarding delay is 15 seconds, and max age is 20 seconds. This means the convergence time, by default, is 50 seconds, nearly a full 1 minute for production traffic to begin flowing through the network. So now, what happens when a topology change occurs? If you weren't aware before, a topology change is describing a bridge or link failure, causing the spanning tree topology to change. In that case, the process described here is followed. The bridge attached to the failure will transmit a topology change notification, or TCN, every 2 seconds until it receives an acknowledgement from the root. When the root receives the TCN, it will set the topology change flag on its BPDUs, causing the switches that receive the BPDU as it propagates to change the max aging time of the max in the forwarding table to the forwarding delay to ensure traffic isn't forwarded incorrectly and not delivered. Now, to wrap this up, let's review a couple of the drawbacks of the vanilla 802.1d spanning tree protocol. As we've seen, STP is quite slow to converge and to react to topology changes. When including that a port in a blocked state can wait an additional 20 seconds before transitioning to a listening state, the port can take a total of 50 seconds to transition from blocking to forwarding. Far too slow to be acceptable for modern networks. Another drawback is that the protocol relies on the root bridge to dictate the topology and changes in topology by setting the TCN flag. As we'll see in another lesson, a later iteration of spanning tree protocol allows all participating bridges to participate in topology changes, allowing for much more rapid convergence. I appreciate you taking a deep dive into 802.1d spanning tree protocol with me. I hope that this has been informative for you, and I would like to thank you for viewing.